Okay, so we are live. Thank you very much for showing up at this today's Pearls of Computation talk, in which I will try to give you an introduction to the work of one of the three female Turing Award recipients, Barbara Liskov. I chose her, well, because she's one of the very few female Turing Award recipients. Her work is perhaps not as well known as it should be, and some of the meta lessons I think that I will try to introduce and that recur over and over again in her work might, I think, be of interest to a wide audience. So let's start with introducing you to Barbara Liskov. That's the photo that she has on her webpage. She's a young lady of age 76. She will be 76 in November, I believe. But as I will show you at the end, she's still very much active, and she's still actually doing work and publishing papers. So that's another example to follow. She was named amongst the top 50 faculty members in the sciences in the US in 2002. There were 7 female, I think, MIT faculty who were named in that list. She was one of those. And that happened before the awards, the important awards started sort of snowballing. She got the 2004 IEEE John von Neumann Medal. Then in 2005, she was awarded an honorary doctorate at ETH, together with Don Knuth at the same time, and other Turing Award recipients. She received the ACM Turing Award in 2008. In 2008 was a harvest year for Barbara Liskov in terms of awards, because she also received the ACM SIGSoft Impact Paper Award for a paper called Abstraction Mechanisms in CLU. CLU is a programming language that will feature later on in the talk. She introduced this programming language, which was very influential. And the keyword abstraction was in the title of the talk. It was also in the title of the talk that she gave when she received the Turing Award, which is online, and I encourage you to have a look at it. In fact, several of the ideas for the slides that I will be using come from that talk. In fact, I could just as well play Barbara Liskov's talks for you, and that would have been much better for everyone. But I mean, actually, I'm not an expert on the line of work that Barbara Liskov did. This has not stopped me before from giving presentations, and it's not going to stop me now. Another award that she received in 2008 was the ACM SIGPLAN Programming Languages Lifetime Achievement Award. Now, for those of you who don't know what these SIG things are, so the SIG stands for Special Interest Group, and the ACM has several such special interest groups. The SIGPLAN is the special interest group on programming languages. SIGSoft is the special interest group on software. So these are some of the awards. Now, at the end of the talk, I hope that you will be able to answer at least these 3 questions that I'm going to put up on this slide. In fact, one of them I will answer straight away. So if I ask you, what has Barbara Liskov done to receive the Turing Award? What would your answer be? Of course, I've already told you that she designed a programming language called CLU. But
there's this Liskov principle.
Yes, okay. One of the people in the audience is saying there is the Liskov principle. In fact, there is the so-called Liskov Substitution Principle that is important in types. In fact, that's a principle that I think all of you know. It's a principle that she stated in an invited address that she gave at UPSLA, a sort of an object-oriented languages kind of conference. Of course, she didn't call it the Liskov Substitution Principle herself, and she was very surprised when people started sending her emails asking her to explain to them the Liskov Substitution Principle. She didn't even know what they were referring to. Well, actually, when they explained what they were referring to, she actually realized that she had actually enunciated the principle herself. So this is what the sort of part of a citation for a Turing Award. She revolutionized the programming field with groundbreaking research that underpins virtually every modern computer application for both consumers and businesses. Her achievements in programming language design have made software more reliable and easier to maintain, and they're now the basis for many modern programming languages. So given this statement, it's kind of perhaps surprising that if I ask our average computer scientist or our average student, what did she do? The answer is perhaps, well, we don't know. So we should perhaps teach more of the things that underpin her work. That's one of the reasons why I decided to talk about her work. Her PhD thesis, what did she do her PhD thesis on? Well, that's something I will tell you later on. It was actually in AI. And at the end of the talk, I hope you will be able to answer, if you don't know already, unlike Alvaro, what the Liskov Substitution Principle is. She did many more things than what I'm going to cover. In fact, what I'm going to cover is mostly related to programming languages. But at a certain point onwards, she actually mostly worked on systems. In fact, she considers herself, I think, more of a systems person than a programming languages person. But a lot of the systems work that she has done, basically, I think all of the work that she's done in systems is grounded in the idea of abstraction. And she has designed programming languages that actually embody the kind of abstractions that she felt, and she still feels, I believe, are the key to good software development, be it in systems or elsewhere. So another thing that actually Barbara Liskov has done, and I think, what she should be known for, is her pioneering role as a female computer scientist. She was amongst the first as a female computer scientist in many things. So for instance, she was one of the earliest PhD graduates in computer science of any gender. And according to some sources, she was the first ever female PhD in computer science. She was the first woman in the MIT computer science faculty, 1972. That was the year when I think Nancy Lynch, who's now a famous professor of computer science at MIT, finished her PhD with, under the supervision of Albert Meyer. She was the first woman to receive the IEEE John von Neumann Medal, second of 3 female ACM Turing Award recipients. Francis Allen and Shafira Goldwasser are the other 2. She was the 3rd out of 4 women to receive the ACM SIGPLAN Programming Languages Lifetime Achievement Award. So actually, it seems like SIGPLAN is better at honoring the work of women than other SIGs and the ACM Award. Perhaps more women work in programming languages, I don't know. She also served as associate provost for faculty equity at MIT, where she played a major role in in making sure that there were more women recruited to the faculty, and not just women, also minorities. And she also helped them to manage their life and their career. In fact, when I was reading an interview with her, when she said, well, as a young woman working in computer science, as a programmer, as a PhD student, then going back, especially when she was working as a programmer at the Micri Corporation and at Harvard before joining the MIT faculty, I always thought, she said, that at some point I would start a family and stop working. But when I was working at Micri, I was more and more thinking that, well, actually, I was not going to do that. And then she started as a faculty member, and she never looked back. But actually, she did have a family, and her son is also a computer scientist, a guy by the name of Moses Liskov, who also works at the Micri Corporation today during work in security. And he's also a PhD graduate from MIT. So you can see trends in families here. Another reason why I wanted to tell you about Barbara Liskov's work is because in some sense, she helped me unwillingly and unknowingly when I started my career. My first academic position, which involved teaching, was at the University of Sussex, the university where I did my PhD, where I was hired in September, October 1992. And I was given the job of teaching a software engineering course. And of course, when I was interviewed, they told me, okay, you will be willing to teach courses in software engineering because this is what we need. And I said, yes, of course I will. Well, I mean, in interviews, you lie as needed. Well, I mean, you don't lie in a way because you know that if they hire you, you actually have to teach the software engineering course, which I did. But I was also given the job of designing a software design course, which didn't exist before. Note the recursion here. Designing a software design course. And in fact, as I had absolutely no idea how to start designing a software design course. So I was actually in an endless loop recursing on the design process until I stumbled across this book by Barbara Liskov and John Goodtag, Abstraction and Specification in Program Development. And there you can read part of the blurb from the book, which is now unfortunately out of print. And this is, I copied from the Amazon page for the book. And as soon as I read that, I thought, well, perhaps there's something I can, this is something I can use. And in fact, I sort of designed the course. Don't ask me now what was in it because I've forgotten. It was more than 20 years ago. And I haven't taught a software design course again after leaving Sussex a while back. But anyway, sort of, there were things in this blurb that really captured my attention. The fact that sort of this book gave a unified treatment of the techniques of abstraction, specification, and why they are the linchpin for developing good programs. And they place a lot of emphasis on the role of data abstraction to produce highly modular programs. So this, I still use actually some parts, photocopies of this book that I think I made in Aalborg at some point when I need examples to teach Hoare logic. Question? Okay, Magnus in the audience said sort of use this book as a student. Yeah, so well, I was not alone. Magnus agrees that this is a good book. In fact, sort of, it really sort of saved my skin, metaphorically. Sort of, so at least it stopped the endless recursion that I was going through in designing this course, or thinking how to design this course. So now let's go back to Barbara Liskov. Sort of, let me start by telling you what she did at the start of her career. Okay, sort of, she's about to turn 76. She was born in California in 1939. She did a Bachelor of Arts in Mathematics at the University of California, Berkeley in 1961. And at that point, she decided that she was going to apply to graduate school. She applied to graduate school immediately. Now, 1961, I was born in 1961. So for what it's worth. She applied to graduate school, and now she thinks, so in an interview with her that I read, she says, I was very naive at the time. Now you think, why was she naive? Well, she actually got back as a reply, no, we don't admit women in the graduate program. Now think, US 1961. Okay, so what did she do? Well, she took up a job as a computer programmer at this Mitre Corporation, which is a corporation that still exists. In fact, her son is working there now. It's in the proximity of MIT, in Bedford, Massachusetts. And they do sort of work for governmental institutions. It's governmentally funded research center where they solve problems somehow for people. Today, perhaps they're doing a lot of cybersecurity. Well, not perhaps. They do a lot of that, but they also do other things. The Lincoln Center is another such center that does governmentally funded research. Then she decided to join a project on natural language processing at Harvard. At that project, they were trying to develop software that would translate natural language into a language that the computers could understand. And you know, those were the pioneering days where people really thought that that problem could be solved in a few years. Well, it took substantially longer, as we learned from Ulvar last week. In fact, perhaps we are approaching the solution to that problem now, but more than, well, 50 years later. Eventually, she decided to go back to academia, and she was admitted to a PhD program at Stanford University, where she actually received a PhD in 1968, 7 years after graduating from the University of California, Berkeley. And the topic of her PhD was a program to play chess and games. So she did a PhD in artificial intelligence, doing sort of, well, writing this program in Lisp to play chess and games. But already halfway through her PhD program, she realized that she was not really interested in AI. She was interested in systems, programming languages. Why? Well, for several reasons. I mean, first of all, she says that she wanted to do work that had somehow more immediate impact. Sort of the AI enterprise was something that she realized would take decades to have an impact. The problems were simply too hard. And moreover, she was really interested in the programming aspect. She was really interested in building systems. And in fact, she did build a system to play endgames in chess. So after she finished her PhD, she went back to the Mitre Corporation to work on a program that they'd already started. They had a machine, which I think was called the Interdata 3, which was a small machine that she seems to remember it had 16K of read-only memory or RAM or random access memory. So it was one of the machines of that time. And one of the things she wanted to do was to see, this was a microprogram machine, which is something that I actually learned when I was a student, sort of microprogramming. Today, I don't think we teach it to our students anymore. Today, firmware is probably something a little bit higher level than microprogramming. But you can think of it as some kind of early days RISC machine, where you would use this small instruction set to build macro programs on top of that then could be used to build higher level programs. And what she thought was, okay, sort of let's see what we could use this machine for. This machine was called the Venus, and she developed the Venus operating system. And the idea is that this operating system should allow some kind of multi-user use of the machine. So it would be a multitasking, multi-user machines. Now, this was a substantial software development enterprise. I mean, sort of building an operating system is sort of hard now, but you can imagine, I mean, these were the days where even building a compiler was sort of black magic. Whereas today we teach it to undergraduates. At that point, sort of really you were doing something that perhaps nobody had done before. So Barbara Liskov sort of did something that I think everybody should do. So she was approaching a difficult programming job, so she asked herself the two key questions. How should I design this program, this operating system? And how should I structure the program so that I can sort of be somehow at least convinced that it works in some way? So her approach was to read the classics. Well, she did the work, and then she read the classics afterwards, just to see how her work compared with what Dijkstra was proposing. This was the time when sort of Dijkstra had recently published this letter to Communications of the ACM about GoTos considered harmful, where there was this debate about structured programming, where David Parnas was introducing the concept of a module as a way of structuring programs. I don't know whether we teach this stuff today, sort of it's probably prehistory. Barbara Liskov said that when she was practicing her Turing Award talk to the students, and part of her Turing Award is going through some of these classics, she was shocked, flabbergasted, because none of her students actually knew any of these papers they had read. None of them had read any of these papers. So after reading the classics, she realized that she'd been designing the operating system somehow based on ideas that were close to, but not quite the same as the ideas that the classics were proposing. And the approach that she was following was essentially the good old problem-solving approach of dividing and conquering. So what you do is you define the operating systems by breaking it out into subcomponents, and then design the subcomponents by breaking themselves down into subcomponents, and so on, until each one of the individual functions that the component has to program is so simple that you can actually program it in essentially one function. This is what people today call a top-down software development approach. So let me give you some quotes from the paper that Barbara Liskov, this was one of her earliest papers, where she presents the design methodology that she had used for building the Venus operating system. So here's a quote from early on in the introduction. I'm not going to read it to you. You can read it by yourself, but I think this should ring a bell. This could be written today. Okay, any user of a computer system is aware that current systems are unreliable because of errors in their software components. We all realize that there is a need for reliable software. Unfortunately, so far, we've been unable to produce it. And whole operating systems are released to the public with hundreds of errors still in them. And then you tell Microsoft about the problem, or you send a software crash to Linux or whatever else. So her initial work was grounded in a period where there was something that people call the software crisis. In fact, I mean, it's not over. We've been in a software crisis for 50 years or 40, whatever that is. And what she says is that, well, basically, we were at the time where our ambitions were much more advanced than what we were able to produce. Well, that's human nature, isn't it? At the time, when she was writing, people were trying to write sort of software systems that were way too ambitious for the type of techniques, the type of programming languages, the type of tools that they have, and in fact, for the machines that they had to run things on. And hardware was expensive. So what people tended to do was to say, okay, let's buy the minimum amount of hardware that we can afford, and then let the software do all the rest. Because nobody had actually quantified at that time how much the software costs, which is much more expensive than the hardware at the end of the day. Because the hardware you buy once, the software you need to maintain to correct all the hundreds of errors, and you need to refactor. So the software has a long lifespan. In fact, some of the pieces of software that people wrote then are still in use in some form or another. Use another quote. Just to make you ask yourself today, one of the big buzzwords is test-driven development. You should develop your system so that sort of you think at all times, how am I going to test it? Is this a new idea? Well, this is a quote from the 1972 paper where she says, well, okay, we have debugging to ensure or to check whether our systems actually do what they're supposed to do. But in order to debug, I mean, sort of debugging is kind of a last resort. She was a follower of Dijkstra. She said, okay, debugging can never guarantee anything. And in any event, sort of to do debugging, you need tests. And when should you design tests? Well, what she says is that the best time is to keep the need for exhaustive testing already in mind at design time. Because unless you do it from the design time, you're going to be in trouble later on when you need to test. Well, that's the idea of test-driven software development in a quote from a 1972 paper. So what idea did she use in structuring the Venus operating system? Well, she used something that she called partitions. She goes on record as saying, well, I could have used the word module, but module sort of already had some kind of meaning, so I didn't want to overload the term. And I like sort of the idea of partition, because partition in mathematics, a partition of a set, means that you're actually dividing the set into disjoint components. So what is it that she says? Well, essentially, I want to organize my system as a hierarchy of partitions. And the idea is that each partition represents one level of abstraction. It consists of some functions that share the same resources. Now, connections in control are going to be limited by the idea that sort of lower level partitions do not know what the higher level partitions do. Okay, a partition only has access to stuff that is in partitions below in the hierarchy. And data connections between partitions are limited to calling functions, operations, that the partitions export at the interfaces. So in other words, different partitions have encapsulated data. They have some kind of system data that they hold private. The only way that other partitions can access the system data of another partition is by calling functions. And moreover, partitions should be logically independent from one another. The only interaction is via the function and via sort of the hierarchy. Now, let me ask you, does this sound familiar? What does this make you think of? Some people say object-oriented programming. Modules. Abstract data types. So I'm on an older generation, you see, sort of, I believed in abstract data types at some point. Now, this is a technique, this is a methodology that she used, that Barbara Liskov used to design an operating system. So she asked herself, okay, sort of operating systems are pretty specific types of software. Can this technique be used to build in arbitrary programs? Okay, sort of with modern eyes, we can say, well, sure it can, but that's the benefit of hindsight. She wanted to see, sort of to present these ideas that she had used in such a way that programmers might benefit from them. And this is how the concept of abstract data types was born. She started working with a PhD student at MIT, Stephen Zils, who was, as she says, not your average PhD student. He was doing a PhD part-time, but at the same time, he was actually working as a programmer at IBM. So he was a fairly mature PhD student with a lot of practical experience. And they started thinking hard about sort of how this idea of partitions could be brought to bear to standard software development. They wrote a paper based on the ideas where they introduced the concept of abstract data type. So what's an abstract data type? This is what they call the cluster with encapsulation. So it's a cluster of operations that encapsulates the data on which the operations actually operate. So an abstract data type consists, first of all, of a set of operations. Note, it's not a set of objects, first of all. It's a set of operations. That's the first thing. Of course, the operations have to operate on some objects, but the crucial thing is that the operation provides the only way of using the objects. Users of the abstract data type do not have any access whatsoever to how the objects are implemented. The only way that they have to use the object is to use the operation, to call the appropriate operations. In this paper, they also introduced polymorphism, which is fairly advanced stuff for 1974, even though at that time several people were thinking of ideas related to polymorphism. John Reynolds was one of them, Girard in the setting of logic, and other people. But sort of they were the closest, they, in the sense of Liskov and Zils, were the closest to the programming language community. And it makes a lot of sense. I mean, if you're defining a data type stack, for instance, would you want to define a stack of integers, a stack of characters, a stack of whatever else. Well, the actual operations of the data type are always the same. Pop, push, check whether the stack is empty. So why don't you define a stack of objects of type T? Whatever T may be. And then when you create an object of type stack, you create a stack of integers if you want, by sort of instantiating the general polymorphic type. They also hoped, because they didn't know whether they could actually achieve it, they were hoping for static type checking. One of the things that Liskov did, remember, she wrote her PhD thesis on a program to play endgames in chess. And she wrote it in Lisp, which does not have static type checking. So she really appreciated the good things about static type checking. Every time she was getting runtime errors at that time, that a simple static checking in the compiler, well, Lisp is interpreted, but this simple static checking in the compiler could have figured it out for her. She increased their confidence. The static type checking is something she wanted. And they also called for exception handling. That's something that today we take for granted, but it was not, it was a totally new idea at the time. There were other people working on languages for data abstraction with exception handling, but not that many. And it makes a lot of sense, because perhaps the programmer might be foolish enough to call a pop operation on an empty stack. Well, what do? You make everything crash? Well, perhaps it's a good idea to have some exception handling just in case that happens. So one of the things that Barbara Liskov did was to popularize the idea of abstract data type. And you can see that the partitions that she was using in Venus are very closely related conceptually to the notion of an abstract data type. So she thought, programmers could actually benefit by using data abstraction, and abstract data type are a way of achieving this type of data abstraction. This could help programmers modularize their programs. This means that the implementer of the data type could actually change the representation of the objects, but if the operations keep behaving as they should, then the users of the data type should not change their programs. That's the key thing. You want to rely on encapsulation in order to make your programs modular. So, having introduced abstract data types, she thought, okay, how can I actually make programmers use them? Well, the best way for her was to say, okay, let's produce a programming language where abstract data types are actually first-class citizens, so that programmers who program in this programming language will have to use abstract data types. This is a quote from her. Basically says, I always had a very strong idea of what good programs and what were bad programs. So by producing this language, I wanted to make it easy for people to write good programs. Of course, any language designer cannot prevent programmers to do a crappy job at producing programs. But she says, I wanted to make it as difficult as possible for them to do so. Now, language design is a very complicated thing. I never designed a real programming language myself, and I most likely never will. But there are many things that you have to take in mind. So you want a programming language which is expressive in the sense that its users can use it to do the things that they want relatively easily. It should be simple to use. It should have good performance, otherwise people are not going to use it. And for them, it should be minimal in the sense they didn't want to overblow the language with all kinds of operations. And safety really refers to the fact that they wanted the compiler for this language to do as much static checking as was possible at the time. So some restrictions. she decided early on that the world was already complicated enough without concurrency, so no concurrency. That's fair enough. I mean, also because it was orthogonal to the use of data abstraction, encapsulation, abstraction, which is what the idea that she wanted to push. Of course, no go-tos. Everything should be structured programming. And no inheritance. Now, at that time, in a parallel enterprise, people were designing Smalltalk. In Norway, people were working on Simula. So sort of object-oriented programming languages were coming to the fore. I don't think that people were actually aware of each other's work. And inheritance plays a fundamental role in object-oriented programming. But it's fair to say that a lot of people actually don't understand inheritance. And I am one of those, probably. And in fact, inheritance is a pretty tricky thing. So she decided not to have it. So in fact, the programming language that she designed, which is called CLUE, remember this impact paper, abstraction mechanisms in CLUE? CLUE is the programming language, and it's the beginning of the word cluster, which is the word that they use, the keyword that they use for the abstraction, the main abstraction mechanism in the language CLUE. It was the cluster which you can think of as some kind of class or some kind of specification of an abstract data type. So the idea of CLUE, which is the language that underlies the book that I showed you before, Abstraction and Specification in Software Development, was that it's an object-based language. It's not an object-oriented language. Remember, no inheritance and all that stuff. But it should somehow support naturally the development of a program by this stepwise refinement approach that I said before. So you start by having the program as an abstraction, then you break it down into subprograms, and you keep doing so until, well, you have simple functions to implement. So the design decisions that they made, as she said, was, as she says herself in her talks, were somehow rooted in the fact that she had all this Lisp experience. So this was a language with garbage collection, like Lisp. And memory management was heap-based. And the reason why she wanted it heap-based was that because the language should support separate compilation, which is much easier to do if you don't have to allocate stuff on the stack. Because otherwise, you don't know how much space a program is going to need. If you compile programs separately, well, how much stack space are you going to allocate for this separate compilation? This is also another fairly advanced feature that even modern languages sometimes today struggle with. Static type checking and no block structure. Now, we are all used to block structured programming languages. I mean, sort of, if you think languages in the ALGOL tradition, a program consists of a large block that then has nested subblocks. Now, in their language, sort of the functions can use blocks somehow, include sort of the operations. The code for the operations can use blocks, but the whole program is not thought as a single block. It's a bunch of abstractions. The mechanisms that the language supported were the clusters that supported essentially data abstraction. These are the abstract data types, the classes. Polymorphism, exception handlers. So here's an example. So that if you have a polymorphic data type set, a set of objects of type T, and you have a function that says, well, choose an element of that set, well, perhaps the set you're choosing from actually happens to be empty right now at runtime. So except when, that's the exception handler. Except when the set is empty, in that case, you do ... And this was one of the early language with iterators. You want to do the same operations on all elements of the data type that you are working with at that time, so you just have an iterator. So all the stuffs, a lot of this stuff you have in programming languages today, but this is a language from 1974, 1975. And actually, there is still a web page that you can access from the programming language group at MIT, where you can probably play with Clue if you're interested. You can see what Clue programs actually look like. Now, what next? Well, time passes, and the world becomes more and more distributed. So, and naturally, remember, Barbara Liskov considers herself as a system person, where actually sort of concurrency, parallelism were always there. Now, the extra thing was distribution. The extra thing was that there were the beginning of what became the internet. So how do you program distributed applications? How do you program applications where you have your programs running on different nodes in a network, where failures can occur, where the world becomes nasty, even nastier than it was before? So she set about to developing a programming language, which they called Argus. Took them about 6 years. That's the time span in which they worked on it, for the creation of distributed programs. The idea is that an Argus program consists of a collection of objects, which they call guardians. And you can see that there is always this idea of encapsulation somehow. Sort of a guardian is an object that encapsulates a collection of related procedures, which they call handlers, which are run in response to remote requests. Argus guardians are running on nodes in a distributed system. And in fact, the Argus system also has facilities for automatically handling failures. So what happens if a guardian actually gets killed because of a failure, or perhaps a temporary failure on the node where the guardian is actually executed? And so they have some kind of rollback mechanism so that the guardian goes back to some sort of consistent state. Fairly advanced stuff. Another interesting thing that the Argus language had was that computations, it had a linguistic facility, and I think it was probably the first language to have that, for atomic transactions in a programming language. So computations are run atomically. So when somebody requests the execution of a handler from a guardian, for the process requesting the execution of the handler is a null or nothing thing. It either succeeds in producing a consistent state, or it doesn't. There's nothing in between. So which is something which is familiar from databases. But they were the first ones to have it in a programming language. Another thing that should ring a bell by now is the fact that guardians do not expose to the other guardians the structure of the data, of their private data. The only way that the other guys have to access the data of a guardian is by calling handlers. You can see it's the same ideas over and over again, but now in a distributed setting. So not surprisingly, this language was actually very much based on clues syntax and on clues semantics. Well, I mean, if you have a winning team, you don't change it, do you? Well, I mean, you can change it at your own risk. Now, this language was developed with a bunch of people at MIT who were then young researchers. I'm sure Magnus knows at least one of them. There are two names that I've highlighted in red. Maurice Herlihy is a very big gun in distributed computing these days. Well, he has been for a while, not just these days. Just to give you an idea, he's the guy who coined transactional memory, amongst other things. And Robert Scheifler is perhaps less known, but if I say X Windows, does this ring a bell? Well, he's one of the guys who was responsible for the X Windows system, and he's one of the guys who developed the sort of Genie system at Sun Microsystems later on. So you can see that some of these people then went on to have pretty good careers and impactful careers themselves. Okay, that's not all over. I mean, sort of, I told you about this. One of the things that Barbara Liskov was interested in, apart from going distributed, was this idea of types. I mean, remember, sort of, there's always this focus on the static type checking. So types are important in all of our work. Now, in object-oriented programming, there is this notion of subtyping. Okay, when is it that you have a class which is a subclass of another one? Now, a lot of these definitions of what it means to be a subclass are syntactic. But these Barbara Liskov always found unsatisfactory. Why? Well, this is an example from her. Suppose, I mean, you have an abstract data type that represents a queue, and another abstract data type that represents a stack. There is no reason why the stack operation should be called pop push. They could be called enqueue, dequeue. But then what's the difference between a stack, at least sort of at the interface? What is the difference between the data type stack and the data type queue? Well, they're actually the same type, syntactically. But semantically, well, they're going to behave very differently, and the programmers are not going to like that. Because if they expect to interact with a stack, and what they get back is something that behaves like a queue, they are in trouble. So what she said was that the notion of subtyping should be behavioral. And she encapsulated that in a statement that then became known as the Liskov Substitution Principle. Objects of subtypes should behave like those of supertypes if used by supertype methods. So in other words, I mean, if I have a method that operates on the data type citizen, and I run that method on something of data type student, then that method should behave as if it was applied to a citizen, because a student is a citizen. And okay, there is a formal version of it that she stated with Jeannette Wing, another person who then went off to have a very famous career. So this is all to make sure that inheritance does not break encapsulation of data. There are actually object-oriented languages, including Smalltalk, in which inheritance actually allows subtypes to have a look at the actual implementation of data of a supertype, which is something that she doesn't like at all. And understandably so, because it breaks modularity somehow. That shouldn't happen, even though in several languages it does happen. So I said she's soon to be 76. So her work doesn't stop there. After that, she developed an object-oriented database system, which she called Thor, by the way. That's a nice Icelandic or Norse connection there. She did work on information flow security. So she's been doing a lot of stuff. But from that point onward, she really mostly was in systems. And she still is in systems. In fact, when the announcement for my talk was sent out, I get a message from Ulvar Erlingsson, who tells me, you know what, I'm sitting next to her at the conference, the symposium, the biannual symposium on operating systems in Monterey, California, on operating system principles. So she was there this week attending the conference. That's what you do when you're approaching 76. So I asked Ulvar, why don't you ask her what she's up to these days so that I can tell people in the audience, give them some fresh news. So these are two of the things that she's working on today, courtesy of Ulvar and also of Barbara Liskov. Thanks, Barbara, in case you're listening to me, unlikely, I know. She's working with people at Harvard, a very famous guy actually, Hedy Kohler, and she's going back to database systems, parallel database systems, which she wants to make out high throughput. And how does she do that? Well, she's planning to use, they are actually using, they have papers on that you can read, RCU primitives. So these are primitives that comes from Linux, actually. They're one of the synchronization primitives for Linux that she's trying to use because they give an epoch-based view of the development in time of the database system. She's trying to use these synchronization primitives to improve throughput in parallel databases. She's also still working on types. She's trying to develop easy-to-use type systems for languages that mainstream languages that give some of the flexibility of stuff that functional programming languages like Haskell give via sort of what they call higher-order generics. So she's planning to do something close to what I think in Google Go is called duck typing. And it's again a kind of behavioral type of thing. Duck typing is based on the metaphor that if you have something that walks like a duck, quacks like a duck, it's a duck, behaviorally, at least. And it's sort of close to this subtyping idea, behavioral subtyping. It's the behavior that matters, not so much the syntax. So at the end of the day, she's still looking for good abstractions for today's computing jobs. So let me summarize what I think is the message of at least some of the part of the work of Barbara Liskov that I surveyed today, and it's got to do with abstraction. Here I quote one Turing Award winner and two pearls of computation that we've had so far, because we started this semester with a talk by Magnus on Christos Papadimitriou. Well, this is a quote from Dijkstra's Turing Award contribution, which he entitled The Humble Programmer. Basically, the bottom line is that programming is hard. We should approach it as humble programmer. We should stick to modest and elegant programming languages because our brains, human brains, actually cannot take very much more than that. And we should appreciate approach the programming job with a full appreciation of its tremendous difficulty. It's really hard. And not surprisingly, we make mistakes. It's actually surprising we get it right more often than not. And this is a quote from Christos Papadimitriou, who basically says that in computer science, abstraction is inevitable. The stuff that we're dealing with is so complicated that we really need to have significant abstractions in order to manage it. You don't want to reason about the machines in terms of the electrical devices running inside or the quantum phenomena that are in there. You will not get anywhere. You need abstractions. So he says computer theory in the broad sense, namely in the sense of using abstraction to understand sometimes the kind of things that we want to do, is not only justified, possible, or desirable, it is inevitable. So perhaps if we keep this in mind, we will all do a better job starting from me. So in conclusion, I think I've convinced you that Barbara Liskov has had impactful ideas in programming languages, operating systems, computing. I haven't touched about information flow security and much of her work on distributed systems. But in all of these areas, she has wielded the power of abstraction. She has always tried to find appropriate abstractions that would make the work of the average computer science easier. Then she says, I cannot prevent people from screwing up, but at least I try to make it as hard as possible for them to do so. And I really hope that sort of the young generation of computer scientists that we have here, they could sort of at least carry with them the idea that we should be ambitious but humble at the same time when we design our systems, and that we should approach our jobs, programming jobs as computer scientists, by trying to use whatever abstractions, whatever specification. I mean, these days, top-down is a swear word in the age of agile development, where you're supposed not to have any specification whatsoever. Well, I don't believe that's a very good idea, because if you don't have any abstract idea of what you're going to do, how do you know what you're actually going to do? And how do you know, once you've achieved, once you've finished with your program, whether it really does what your original intentions were? So thank you very much. That's the end, and I'm roughly on time. If there are any questions, we can take them offline if you want. Okay, Alvaro?
So, since you mentioned that she's now perhaps working in this combining higher order with subtyping, so how do you feel, or how do you think she was feeling back when she introduced her view of abstraction? How she was feeling about that combination and paradoxes that could be there when you take.
Yeah, to be honest, so the question is, since she's now working on combining higher order, so to be honest, I don't know. I think the best answer would be to read this paper on lightweight, flexible, object-oriented generics that is hyperlinked from the slides, and that she published, I think, last year, or this year, actually, in the proceedings of PLDI. So this will give you the answer to the question. I haven't read it myself, sorry. But so she's basically sort of trying to have some lightweight approach to adding this sort of higher order generics to object-oriented programming languages. And then, I mean, for some people, Haskell is actually a mainstream programming language, so perhaps that's the one you should use. But that's then it becomes nearly a matter of faith. I mean, sort of. So what she's trying to do, again, she's keeping her eyes open. She's trying to import into object-oriented languages some things that obviously she thinks are good from the functional paradigm. And I actually also have a link to the parallel database work in case you want to see it. But if you go to DBLP, you will be able, so it's these are the recent papers on our DBLP page, which you can read at your leisure. So the bottom line is she's still very much active. Okay, I don't want to keep you any longer. Thank you very much again, and